In 1838, biology had a revolution, and it started with a better microscope. Scientists like Schwann looked through the lens and discovered that every living thing is built from cells. That single idea, cell theory, turned biology from vague observation into a real science. In 2020, a team at OpenAI argued that neural networks are having their own microscope moment. The lens is a technique called feature visualization, and what it reveals inside the network is just as structured as cells under glass. Their paper is called Zoom In. So what is this microscope exactly? It's a technique called feature visualization. To find what a single neuron is looking for, you start from random noise and gently tweak the image, pixel by pixel, to make that neuron fire as hard as it possibly can. The picture it settles on is, in a real sense, the thing that neuron most wants to see. Run it across a network and you get these psychedelic, dreamlike images. But look closely, and they're not noise at all. They're full of meaningful structures, text shapes, eyes, whole objects. This is the lens we'll use to look inside. Zoom In makes 3 bold, testable claims about how neural networks work. 1. Features. The network is built out of meaningful, understandable units, not an inscrutable blur of numbers. 2. Circuits. Those features are wired together by the weights into genuine algorithms you can read. And 3. Universality. The same features and the same circuits show up again and again across completely different models. If these claims hold, we can study a network the way a biologist studies an organism. Let's take them one at a time. And the beauty is that none of these are vague philosophy. Each one is something you can put under the microscope and test against the actual weights of a real, trained network. Start with features. Pick a single neuron deep in a vision model and ask, what makes it fire? Feature visualization answers by generating the image that excites it most. Do this across the network, and meaningful detectors appear everywhere. Here is a whole family of curve detectors, each tuned to a curve at a particular orientation, alongside related shapes like circles and spirals. These aren't cherry-picked curiosities. They're crisp, repeatable units of computation, and that is the first claim. The network is made of features we can actually name. How can we be sure a neuron really detects curves? And we're not just fooling ourselves. The paper triangulates. The feature visualization looks like a curve. The dataset examples that activate it are curves. And crucially, you can read its weights. A curve detector is excited by earlier curve detectors in compatible orientations and inhibited by incompatible ones. Multiple independent lines of evidence point to the same conclusion. That rigor is what separates a real feature from a just-so story. And the curve detectors arrive as a beautifully organized family. There isn't one curve neuron, there's a whole set, each tuned to a slightly different orientation, together covering every angle. Rotate the input curve, and a different member of the family lights up, smoothly, in step. Mathematicians call this equivariance. The network hasn't just memorized one curve, it has learned curvature as a structured, rotational concept, and laid it out across neurons in an orderly, almost geometric way. Curves aren't a fluke. Here's another vivid example: high-low frequency detectors. These neurons fire at the boundary where a high-frequency, detailed region meets a low-frequency, smooth region, exactly the kind of edge you find between a sharp foreground object and a blurry background. It's a clever, useful trick for separating figure from ground, and the network discovered it on its own. Each clean feature we decode makes the first claim harder to dismiss. Now the second claim, and this is where it gets exciting: circuits. Features don't sit in isolation. They're connected by the network's weights, and those connections implement understandable algorithms. Watch a curve get built. Early, simple curves and lines, in the right arrangement, feed forward and combine into more sophisticated curve detectors, which themselves combine into complex shapes and curvature. The weights aren't random plumbing. They are a circuit, a small program assembled from features. And here's the key move. A positive weight means one feature excites another. A negative weight means it inhibits it. So the connections read like logic, and the network starts to feel less like a black box and more like a wiring diagram. Here's a circuit you can read like a recipe. A car detector deep in the network is assembled from 3 earlier features. A window detector that excites the car at the top and inhibits it at the bottom. A car body detector, strongest at the bottom. And a wheel detector that excites at the bottom and inhibits at the top. Windows on top, wheels on the bottom, body in between, that's a car. The model literally encodes that spatial logic in its weights, and we can spell it out. Circuits can implement clever logic, not just stacking. Take dog heads. The network has a detector for a dog's head facing left, and a separate detector for a dog's head facing right. Each is built from oriented snouts and eyes pointing the matching way. So far, two narrow, pose-specific features. But the network does something smart with them in the next layer. It unions them. A later neuron takes both the left-facing and the right-facing dog head detectors as positive inputs, so it fires for a dog looking either way. That's a pose-invariant dog detector, and the algorithm it implements is simply a logical OR, written directly in the weights. A concept we describe in words, facing left or facing right, turns out to be an operation you can point to inside the network. And again, the story checks out against reality. The pose-invariant dog detector's own feature visualization shows a head you can read either way, and the real dataset images that fire it are dogs in all sorts of orientations. Feature visualization, dataset examples, and the weight diagram all agree. Circuits aren't a metaphor we're imposing. They're a structure we're uncovering. The third claim is the most surprising. Train completely different architectures, AlexNet, GoogleNet, VGG ResNet on the same task, and they independently grow the same features. Look, curved detectors. In every one of them. Like evolution rediscovering the eye again and again, different networks converge on the same solutions. Universality means the things we learn from one model aren't one-offs. They may be general truths about how to see, shared across all networks. It even hints that the same toolkit might one day carry over to the biological brain. Understand a feature once, and you may have understood it everywhere. Now, honesty, it is not always this clean. Many neurons are polysemantic, they respond to several unrelated things at once. This single neuron fires for cat faces for the fronts of cars and for cat legs, three concepts with nothing in common, sharing one unit. If neurons can mean many things at once, how can we ever cleanly read a circuit? This is the central obstacle the paper is honest about. The leading explanation is superposition. The network has more features it wants to represent than it has neurons, so it packs them in, spreading a single clean feature, like a car, across many polysemantic neurons, and overlapping different features in the same units. The curved detectors were the lucky, clean case. Superposition is the frontier, the puzzle that has driven much of interpretability research ever since this paper. Step back and see what zoom in really proposes. Stop treating the network as a black box to guess about, and start treating it like an organism to dissect. Feature visualization is the microscope. Features are the cells. Circuits are the anatomy. And because you can always go check the weights, the claims are concrete and falsifiable, real science, not storytelling. The clean curved circuits prove it's possible. Superposition shows how much is left to do. So that's zoom in, 3 claims, features, circuits, and universality that reframed how we study neural networks. It launched the circuits thread of research, the effort to reverse engineer vision, and later, language models, neuron by neuron and weight by weight. Almost everything in modern mechanistic interpretability traces back to this idea, that inside the black box is not chaos, but structure, waiting for us to zoom in. This was Distill's Zoom In by Chris Olah and colleagues.